Now that we've got a better hand at working with limits, we're going to extend that concept to other special types of limits and talk about something called continuity, which you may have heard in your pre-calc class, but you may not have as well. So sometimes when we're dealing with limits, it can be complicated to see what's happening on both sides simultaneously. So it can be beneficial or even easier to investigate a limit by approaching the x value from just a single side. So we're going to consider a pretty cool function, which is called the Heaviside function, named after a mathematician. If you're into computer science, if you have to go in there, you're going to use this function a ton. But basically, the Heaviside function gives you 1 if x is greater than or equal to 0, 0 for negative values. So ultimately, it's a piecewise function that has a nice jump at 0 itself. So notice, if I go ahead and approach from either side, I'm doing different things. So ultimately, the limit as x approaches 0 for this function does not exist because we don't approach a single finite value. Now, however, if I do look at one specific side, so say I approach from the left-hand side, then it looks like my function is going closer to 0. So when we approach from the left, this function goes to 0. And likewise, if we approach from the right, my y is going to 1. So on the right-hand side, it looks like my function is going to 1. So ultimately, the limits from the left and right exist. It's just the overall double-sided limit doesn't. So what we do is use a special notation. If I'm approaching from the left-hand side, what I'm going to do is indicate that with a minus to say I'm picking numbers less than 0. And the right-hand side, I'm going to use a plus. So in our case, to denote this, the limit as x approaches 0 from the left of h of x is 0. And when we approach 0 from the right for this function, the limit is 1. Okay? So these minus and plus notations indicate the minus means we're looking at values of x less than 0. And the plus means we're looking at values of x greater than 0. Okay? So we're just going to utilize these to add on to our definitions of limits. We write the limit as x approaches a with this minus sign of f of x equals L to say the left-handed limit of our function as x approaches a is L. And then we use this plus sign to say the right-hand limit of our function equals L. Okay. So if I want to figure out my double-sided limit, you need to approach a single finite value, so you need what's happening from the left and right to be exactly the same. If they're the same, your two-sided limit exists. If they're not the same, it doesn't. So ultimately, from these definitions, the limit as just x approaches a equals L if and only if both the left and right-hand limits equal L. So you can kind of read this either way. If this happens, then the left and right-hand limits are L. If these both are the same, then the two-sided limit is equal to L. So that's all that if and only if statement means. Okay? So let's try an example. Let's use the graph to determine if the limits exist or not. And so we're going to start with the limit as x just approaches -2. So I have no indication. That means I'm going to look on both sides. So as we approach 2 and we trace our graph, that y value is approaching 3. So this limit does indeed equal 3. For these other ones, we have one-sided limits. So we're approaching 1 with that minus sign indicating the left. So I'm picking numbers that are smaller than 1. And if I trace the graph here, those y values are getting closer and closer to 2. Okay. Now if I change my side and I put this plus, that tells me bigger than 2, bigger than 1. And if I'm picking numbers bigger than 1, I'm on this part of the graph coming in from the right. So my y values are getting closer and closer to 3. So ultimately, if I don't indicate a direction and I just put 1, that means both sides. This does not exist, since the left and right hand limits are not equal. Okay. Let's try some other ones. Let's find this limit if it exists. And we want to find the limit as x approaches 5 from the right of this absolute value function. So again, anytime you have absolute value functions, break it down to that piecewise function. So you want to recall, if I'm taking the absolute value of x minus 5, it's a piecewise function. You're going to get exactly the thing inside if the thing inside is greater than or equal to 0. You've got to negate the thing inside if that thing is less than 0. Okay? So ultimately, I have these two separate pieces. You can distribute this minus sign out to give you minus x plus 5. And if I go ahead and just add 5 to both sides, that tells us we're on this top piece if x is greater than or equal to 5. This bottom piece if x is less than 5. So ultimately, this top one is the right side of 5 because x is bigger than 5. And this bottom gives us what happens on the left-hand side of 5. So if I'm trying to evaluate the limit as x approaches 5 from the right, I'm right here on this piece. So the absolute value of x minus 5 will exactly be x minus 5. And the inside boils down really nicely. It's 1. If you take the limit of a constant, still just 1. So this limit is equal to positive 1. Okay. Let's try another one. Let's find this limit where, again, we have two different pieces. So I want the limit of f of x as x approaches 3, but you have a problem. It does different things on either side of 3. So when x is less than 3, that would be the left side of 3. X is greater than 3 is the right side of 3. Okay. So since we have different pieces on the left and right hand side of 3, we really need to look at one-sided limits. So we're going to figure out what happens on the left, and we're going to figure out what happens on the right. To evaluate this double-sided limit, these better do the same thing. Okay. So if I'm approaching 3 from the left, that's going to give me the x plus 2 over 2 based on my piecewise function. So I'm going to take this limit. No problems just plugging in 3. So we go ahead, and that gives us 3 plus 2 over 2, or 5 over 2. Okay. Then if I'm approaching 3 from the right, that means I'm picking values bigger than 3, which is this piece here. So I'm going to use this other rule inside my limit. So my function for values less than 3 is 12 minus 2x over 3. Again, no problems just plugging it in. So you would get 2 times 3, which is 6. So 12 minus 6 is 6, divided by 3 gives us 2. So ultimately, since these one-sided limits are not equal, the overall limit does not exist. Okay? And you could take a look at this function. They're really just both lines. You can distribute it out, put them in slope-intercept form, and graph them. So I just went ahead and did that here. As x approaches 3 from the left-hand side, it goes to 5 over 2, which is 2.5. As you approach 3 from the right-hand side, the output goes to positive 2. Okay? So what you kind of want to notice is that at 3 itself, there's this break in the graph. It's actually just called a jump. So this leads to what our idea of continuity is. I don't want this to happen. I want it to be a nice smooth curve. So sometimes when we calculate limits, we can directly plug this in. We've seen this for polynomials, rational functions, for trigonometric functions on their domain. All of those have been continuous because it's been nice smooth curves that you don't have jumps happen at. So we say a function is continuous if the limit as you approach C for your function is exactly the output of your function. So if I look back to this function, as we approach 3 from either side, it doesn't exist. So I have this break, I don't have that smoothness, I don't have continuity at 3. But any other number, if I approach from either side, it goes to the actual output. So I'm good everywhere else. So really, within this definition, we really have 3 things that we need for continuity. The first, the point has to exist. You have to have an output for the function. You need the limit as you approach that number to exist. And then ultimately, those two have to be equal. Okay? So in order for a function to be continuous, they need these 3 things. If one of them fails, we say a function is discontinuous at C. So in the last one, this limit failed to exist on either side. It's discontinuous at x equals 3. Okay? So let's try an example. We're going to determine if this function, which is piecewise, is continuous at x equals 2. So we've got a bit of a problem because when x isn't 2, I've got this function. When x is 2, my output is 1. So really what we need is to figure out, does the limit as I approach 2 equal my output? So when I plug in 2, my output is 1. We need the limit as we approach 2 to equal 1 for there to be continuity at 2. Okay? So we just need to figure out what this limit is equal to. And so if we go ahead and try to evaluate that, we want the limit as x approaches 2 of our function. Everywhere except at 2, my rule is x squared minus x minus 2 over x minus 2. And I can't plug 2 in directly, but I can go ahead and factor that numerator. Factors nicely into x minus 2, x plus 1, divided by x minus 2. So our problem ends up canceling. And this is the limit as x approaches 2 of x plus 1. No issues plugging in 2 now. 2 plus 1, that gives us 3. So ultimately, since the limit as x approaches 2 of our function is not the same as the output of our function at 2, f is discontinuous at x equals 2. Okay. So ultimately, we have a ton of different types of discontinuity, 3 in total. So we're going to go through what each of these look like. This last problem has what's known as removable discontinuity, because if instead I had changed this to a 3, this would be a 3. These two would then equal each other, and my function would indeed be continuous. So what I have is I've got that nice graph, because you would just graph x plus 1, and then it had a hole here that was redefined to be this point. If I just move this up a tiny bit, it would give me a nice smooth graph. So it's removable because I can just redefine that single point to make it continuous. The other types I unfortunately can't do the same thing for. So the next one's called an infinite discontinuity, and basically your function grows unbounded as you approach that number. So the best thing that you can think of is one of our nice functions, 1 over x squared, which we spent a lot of time with. Okay. or x to the fourth, whatever you want to do. It could be x to the sixth. All of these have the same graph. So here, as you approach 0, the limit is going to positive infinity because my function is growing unbounded. So I can't have my function, or my function doesn't exist at 0, so this has an infinite discontinuity because the limit goes to infinity. The last type is a jump discontinuity, so basically the function jumps from one value to another. And that you can think of that heaviside function for. It's 1 when x is greater than or equal to 0, 0 when it's less than 0. Your function literally jumps up at 0. Okay? So there is a jump discontinuity there. Okay? So if a function's not continuous at a point, we may, though, be able to talk about continuity on either side. Because if I approach, say, 0 from the right here, I'm going to the actual output of the function. So I could say it's continuous from the right. So this is our next definition. We say a function f of x is continuous from the left at a number c if, when we do the left-sided limit, it's the output of the function. And then we say it's continuous from the right if, when you do the right-sided limit, it's the actual output of the function. Okay? So let's look at some examples. We've got a nice function here. You can see there are two places at -1 and +2 that we jump up to the next value. So f of x has jump discontinuities at -1 and +2. However, if I consider -1, when I come in from this side, I'm going to the actual function value. So ultimately, when I approach -1 from the left side of my function, it goes to 0, and that is the exact output at -1. So we can say f is left continuous at -1. Definitely not continuous, though, because of that jump. And likewise, if I approach 2 from the right-hand side, and I'm tracing the graph, it goes to the output of my function. So if I take the limit as x approaches 2 from the right of my function, it goes to 3, which is the exact output at 2. So f is right continuous at 2. Okay? So overall, it's still not continuous at that point, but at least you have it from that single direction. Same kind of idea with limits. It can exist from one side, but the overall won't exist. So we can use our idea from all of the nice functions we know to combine functions together to figure out if they're continuous or not. So if both f and g are continuous at a point, k is a constant, then the following functions are also continuous at c. So if I add two functions that are continuous at c, the new function's continuous there. Same thing if I subtract, if I multiply by a constant, multiply by these two. And then the last one, if you divide two continuous functions, it is continuous as long as that denominator is not equal to 0. Okay? So it can be super tedious. You cannot physically check every single point to determine if a function is continuous. Really, we can say a function is continuous on an interval if it's continuous every number inside there. We don't need to check every single number. We can use our knowledge about graphs of functions. So polynomials, rational functions, root functions, trig functions, inverse trig functions, exponential functions, logarithmic functions. All of those, you have spent so much time finding domains of those things. They are continuous on their domain. A polynomial, if you graph it, you don't have to pick up your pencil at any point. You're never going to have that break. Rational function, the only possible bad points are going to be where you divide by 0, which are not included in the domain. Same thing with root functions. All of these are super nice. So in all of them, you can use that direct substitution property to evaluate a limit, as long as that number is in the domain of the function. This is why you spent so much time going through how to find domains between intermediate algebra, college algebra, pre-calculus, trigonometry. We hound that into you because you need that property to be able to do direct substitution, okay? We want continuity for functions. It's definitely much nicer. So let's go ahead and try another example. We're going to find the value of a, so this function is continuous on the entire interval. So basically, what do we have to put here to guarantee we have a nice smooth graph? Okay? And so the only thing that could happen, this is just a polynomial. This is also a polynomial. They are continuous separately on these intervals. The only thing that can happen because it's piecewise is there might be a jump in the graph at 1. So I need to guarantee I don't have this jump, okay? So first, we need to make sure our function has a output at 1. If I plug in 1, we're going to use this rule up here, so we would get 3 times 1 squared. So the output is 3. And this piece itself is continuous when x is greater than 1. And likewise, our ax minus 4 is continuous on its domain. So really what we need is for things at 1 to be nice. And so ultimately, I need to guarantee that this limit equals the output itself here. So what we need is the limit as x approaches 1 from the left-hand side, because this is our unknown piece, to actually equal the output of our function, which is 3. Okay? So the idea is, if I draw a quick little graph in here, 3x squared looks like this. And I'm going to specifically pick when x is 1, so the output is 3. We have this line that we basically don't know where it goes. We want to guarantee we pick an A so it lines up nicely right on top of that graph. So when I approach from the left-hand side, I line up with the output of my other function. Okay? So we need this to happen to have continuity at x equals 1. But I can go ahead and calculate that limit. I'm dealing with that line. I have no problems just plugging in 1 here. So it would be a times 1 minus 4. The output here would be a minus 4. So I need this to equal 3 to guarantee I have overlap between these two. So what we need is a minus 4 to equal 3, which really just tells us a equals 7. So if I change this to 7x minus 4, when I plug in 1, that'll be 7 minus 4. We have the output of 3, and I've got a nice smooth graph now. So we need this to happen to have continuity everywhere. Okay? So anytime you're asked about continuity, it better involve limits in some form or fashion. So the last thing we have to talk about is something that's really nice that results from continuity. And that's our intermediate value theorem, or you might just see it abbreviated as IVT. So what this tells us is, suppose we have a function that's continuous on a closed, keyword being closed, interval. You have y values corresponding to these endpoints. So we're going to let k be some number between those endpoints. We are guaranteed then that there is a number c inside this interval, so the output of our function is exactly equal to k. So that's definitely hard to take in just verbally. Graphically, it's going to be a little bit easier. Suppose this is our function, f of x. It's got some y value corresponding to a, another y value corresponding to b. If I pick any number inside of here, okay, I am guaranteed then that the function will output this number at some point in my interval. So this would be my value of c. I am guaranteed. If I plug c into my function, I get k. Okay. Now if I pick a different function over here, and maybe I pick this value in between f of a and f of b. I am guaranteed at least one number that gives me k as an output. Okay? But really, there might be multiple. Here's another value that gives me k as an output. So we'll call that C1 and C2 now. And there's another number over here that gives me k as an output. So in all of these, the function evaluated at C1 is k. Function evaluated at C2, k. Function evaluated at C3 is equal to k. So I am guaranteed k will be the output of the function at some point. Doesn't tell me about what it is, it just tells me it exists. The thing that's important that follows is we can use this intermediate value theorem to show a function has a root in a specific interval. So if I go ahead and draw a function, and at one endpoint my function is positive, at the other endpoint my function is negative. Because it's continuous, I have to cross this x-axis. So I'm guaranteed that I'm going to have an x-intercept somewhere in between a and b. So since this function is continuous, one endpoint is positive, the other endpoint is negative, the function must cross the x-axis at least once. And here it crosses it 3 times. You're guaranteed at least one exists, you aren't always guaranteed that more do. So let's try this in an example. Let's use that intermediate value theorem to show there is a root of this equation in this interval. So I want to guarantee that this function is equal to 0 at some point. Solving that is way too difficult, but I can guarantee that somewhere in between 0 and 1, there is a solution to this equaling 0. First thing though, is we have a statement right here. Suppose f is continuous on a closed interval. I need to guarantee that happens to even apply this intermediate value theorem. But this is a root function and a polynomial. It's continuous everywhere because it's a cube root. You can plug whatever you want into the cube root. Okay. So since f is a combination of a polynomial and a root function, it's continuous everywhere. And then I want to go ahead and see what happens at my endpoints. If I plug 0 into this function, that's the cube root of 0 plus 0 minus 1, gives me negative 1. And if I plug in positive 1, gives me the cube root of 1 plus 1 minus 1, that's positive 1. So at one endpoint, we're negative. At the other endpoint, we're positive. So since one endpoint is less than 0, the other endpoint is greater than 0, and f is continuous, on that interval from 0 to 1, I have to equal 0 at some point. So I'm going to cross the x-axis. So by the intermediate value theorem, there exists a c in the interval 0, 1 such that f of c is equal to 0. Okay? So kind of picturally what happens here, if you're struggling a little bit with that, when we plug 0 into our function, it's negative 1. When I plug positive 1 into my function, it's positive 1. Because it's continuous, I have to cross through at some point for this function. I'm forced to do that by the intermediate value theorem. There's no way I can just jump up because it's continuous. That's not going to work. Okay? So it's got to be a smooth graph that I've got to go through it. Where that happens, I have no idea. I'm just guaranteed it does. Okay? So be really careful with your write-ups on these things. When you're using a theorem, you've got to make sure those hypotheses are satisfied, like the fact that it's got to be continuous on an interval. And you want to state the name of the theorem you're using to show that result. So just like when we were talking about the squeeze theorem, you had to show certain things happened. The squeeze theorem is what gave you your results. So while you're going through your homework, try writing it up in a similar way that I've written in these notes, because you really need to get good at expressing these ideas and showing your work fully. We don't want to just jump into it and have everything all over the place. We've got a lot more stuff that goes into our problems that we've got to have someone else be able to read it and understand what's going on.